Layer 2 packet switching. At Layer 2 of the Open Systems Interconnect model, switches use ASICs, or application-specific integrated circuits, to break up traffic into multiple collision domains. Switches do not modify packets, nor do they read an entire packet and its payload. Instead, they only read the frame encapsulating a packet. On the other hand, routers, which function at Layer 3 of the OSI, read entire packets and modify their contents as they pass through and are redirected to other subnets and networks. As a result of these differences, Layer 2 switching is processed much faster than Layer 3 routing. Layer 2 switching can be divided into three basic functions. The first is address learning. In the OSI encapsulation process, each packet is encapsulated with Layer 2 source MAC address field data. Each switch then learns and stores the source MAC address of each device connected to each port as that device transmits data through the port. Each MAC address learned is stored in a database called the forward filter table. When you first power on a Layer 2 switch, the learning process takes approximately 50 seconds. Filter tables can become corrupted or inaccurate, and this sometimes requires rebooting the switch and waiting to force it to go through the learning process once again and repopulate its MAC address database. The second function is forward and filter deciding. When a switch has learned the MAC addresses of all the devices connected to all its ports and stored them in its MAC database, it then scans its forward filter table for a port that matches the destination MAC address in the frame's MAC address destination field. If the switch does not find a matching destination address in its forward filter table that is associated with one of its ports, it forwards the frame out all of its ports, flooding them with traffic. However, if a matching address is found, the frame is only forwarded out the port that holds that address, sparing all the other ports unnecessary traffic. This is known as frame filtering. Let's look at the Layer 2 forward filter process. Here we have 5 hosts all connected to a switch. Host A is connected to port 1, host B connected to port 2, host C connected to port 4, host D connected to port 6, and host E connected to port 8. On this switch, when A is first connected, it sends a packet, or frame, and this data frame has a source MAC address field. That source MAC address field is read and then entered into the forward filter database. Now the switch knows the MAC address of host A, or the device connected to port 1. The same thing happens for B. When it's connected, a data frame is sent to the switch reads the source MAC address and stores it in its forward filter database. And the same thing happens with C. When C is connected to port 4 in this case, it sends a data frame, that frame is read, and then the source MAC address is stored in the forward filter database. Eventually, the switch will learn all of the source MAC addresses of all of the devices connected to its ports. Then it can use its ASICs to configure a direct connection between any two hosts, say host C. So if A wants to communicate with C through the forward filter database, the ASICs configure a direct connection, a full duplex connection, and a single collision domain. So A and C essentially have their own little world to communicate. And B, D, and E may also do the same. This forwarding and filtering ability is what makes a switch superior to a hub when processing Layer 2 traffic. A switch is a thinking Layer 2 device, whereas a hub is a dumb Layer 1 device. After a set period of time, if devices connected to a switch's ports do not transmit frames of data, the switch will flush their MAC addresses from its forward filter database, and they must be relearned. This provides the switch with the ability to deal with changing MAC addresses on a single device or changes made by unplugging devices connected to one port and connecting them to another. The third basic function is loop avoidance. Redundant connections are created between switches to implement fault tolerance so networks do not fail when a single connection malfunctions. Because of this, like routing loops at Layer 3, switching loops at Layer 2 can occur. Switches use STP or spanning tree protocol to stop loops while still permitting multiple redundant connections. Uncontrolled Layer 2 switching loops can bring a network down even faster than Layer 3 routing loops. Some of the dilemmas created by Layer 2 loops include 1. Wasted bandwidth. Devices unnecessarily receive multiple copies of the same frame from multiple switches on different segments of the network. 2. Broadcast storms. Switches will flood broadcasts endlessly throughout a network, eventually impeding network communications. Multiple loops within loops of broadcasts can occur, crippling a network. 3. MAC table thrashing. This is where a switch can no longer forward frames due to constantly updating its MAC table with the constantly changing source addresses it receives from frames that come from more than one link and different ports. Now let's take a look at Spanning Tree Protocol, or STP. STP monitors the network at Layer 2, discovering all its links and interconnections. When loops and redundant links are detected, STP shuts them down and prevents the same frame from being forwarded from multiple locations. To do this, STP first creates a topology database using the spanning tree algorithm, or STA. Frames are then only forwarded on the particular links that STP selects after analyzing its topology database with STA. Now let's take a look at the root bridge. STP gets all of a network switches to work together by having them elect a root bridge. The root bridge is decided by the switch with the best bridge ID. The bridge ID is determined by a combination of bridge priority, which can be set on the switch, and the base MAC address, which is the lowest MAC address. Bridge priorities are 32,768 on Cisco switches by default, but this priority can be changed to force the election of a particular switch as the root bridge. Switches communicate and exchange information in the election process and by transferring bridge protocol data units, or BPDUs, between each other. There can be only one root bridge on a network. This root bridge should usually be the core switch, which is the switch closest to the center of your network. Root bridges do not have any blocked ports. When two switches have the same priority value, the switch with the lowest MAC address receives the lowest bridge ID. Remember, whichever switch has the lowest bridge ID determines which switch is elected as the root bridge. BPDUs are transmitted from switches every 2 seconds by default and allow STP to manage switches according to these rules. Let's look at an example of setting the priority. In this case, if I were in user mode, I could type the command enable to go to privilege mode. In privilege mode, I could type config T to go to global configuration mode. There I could select an interface, and once I had selected an interface, say port 2, I could use spanning-tree VLAN 1 priority and then set the priority to anything I want. Say 1 if I want to give it a low priority. I could also use spanning-tree VLAN 1 root primary. Let's take a look at STP's root bridge election process. Here we have 7 switches, and they all have a default priority of 32,768. Switch 5 has the lowest MAC address, so it would be, by default, elected the root bridge. That's because its MAC address is the lowest. Now let's say that we wanted to make switch 1 the root bridge. If that were the case, we could simply alter its priority. So if it were 1 less than the default 32,768, say 32,767, or anything lower, then we could force it to be elected as the root bridge. Now let's look at the root port. STP uses BPDUs to configure a root port on each switch. The root port is a port that is selected by STP because it is either directly connected to the root bridge itself, or it is the shortest path to the root bridge through another switch or switches. When more than one link connects to the root bridge, a port cost is determined. Greater bandwidth results in lower costs. If the cost is the same for multiple links, the link with the lowest port number and bridge ID will be selected as the designated port. This is the port through which traffic is forwarded. All other ports then become non-designated ports and are put into blocking mode. Non-root bridges. Non-root bridges are switches that are not elected as the root bridge. For each of these switches, STP determines a root port which is the closest path to the root bridge. This port becomes the forwarding port, which actually forwards frames. All other ports become non-designated ports and are therefore block ports that do not forward frames. Although block ports do not forward frames to prevent routing loops from occurring, they do receive frames from other switches. Ports managed by STP have 5 different states. The first state is blocking. Block ports do not forward frames but do receive BPDUs. This state prevents looping, and it is the default state of all ports when a switch is first booted. The second state is listening. In this state, BPDUs are received to prevent looping and a port prepares to forward frames without adding entries to the MAC database. The third state is learning. In this state, the port does not forward data frames. Rather, it populates the switch's MAC database or forward filter table with paths learned about the network. The fourth state is forwarding. In this state, a port both sends and receives all frames. When a port is designated as the root port, it enters the forwarding state. By default, there is a 15-second delay as the switch changes between listening and learning mode. This transition must be completed before forwarding can occur. It takes approximately 50 seconds to go from blocking mode to forwarding mode. Finally, the fifth state is disabled. In this state, ports do not engage in forwarding or any other STP process. When all ports on all switches have transitioned to either forwarding or blocking mode, we say that Layer 2 convergence has taken place. This is distinctly separate from and not to be confused with Layer 3 router convergence. In the STP convergence process, all data stops transmitting. Considering this, switch placement and configuration should be implemented to allow the quickest convergence times possible. Also consider that whenever a link fails or a new switch is added, creating a topology change, switches must return to listening and learning states and convergence must reoccur. Let's take a look at the STP convergence and loop prevention process. Here we have 7 switches, and switch 1 is designated as the root bridge. There are multiple and redundant paths in the switch fabric between all the switches and the root bridge. This creates the possibility of a loop. STP will run and calculate the most efficient path for each switch to reach the root bridge. Once it does this, it will place the other ports in blocking mode. Once all of the ports have been placed in blocking mode save the root port, communication is then allowed to take place between the root bridge and the other switches through the most efficient path determined by STP. Now let's take a look at the Portfast feature. Ports between switches should run STP. However, sometimes devices plugged into switch ports experience timeout problems because of the convergence time of STP. Ports to which these devices connect can implement Portfast to solve these issues. Using the Portfast command disables STP on a port. As a result, it will come up instantly instead of taking 50 seconds to transition to forwarding mode while STP is attempting to converge. In this state, the port will not use STP to check for switching loops, so you must manually ascertain whether any port you enable Portfast on will create a layer 2 loop. Here's an example of using Portfast. From user mode, use the command enable to go to privilege mode. From there, use config-t to go to global configuration mode. Select an interface, say port 2. Type the command spanning-tree Portfast. Or to select a range of ports, you could say int range fast Ethernet, say ports 1 through 12, and then also the command spanning-tree Portfast. Note, you must specify trunk if enabling on a trunk port when using virtual local area networks. Two other options you might use to Portfast are BPDU guard. If a port with Portfast enabled receives a BPDU, BPDU guard will disable it to prevent a switching loop. There's also BPDU filter, which removes Portfast from a port and makes it part of STP topology if a BPDU is received. Examples: from user mode, use enable to go to privilege mode. In privilege mode, use config-t to go to global configuration mode. Select an interface in global configuration mode, say port 2, and then use the command spanning-tree BPDU guard enabled to enable BPDU guard, or use the command spanning-tree BPDU filter enable to enable BPDU filter. In addition to Portfast, there's also UplinkFast. UplinkFast improves the convergence time of STP on Cisco switches by allowing the switch to find alternate paths to the root bridge before the primary directly connected link fails. This means a secondary link will be determined by STP and brought up more quickly without having to wait for the normal 50-second convergence time. This feature should only be enabled on switches with blocked ports, alternate root links, and extensive knowledge of the network's topology. Here's an example of using UplinkFast. First, from user mode, use the command enable to go to privilege mode. In privilege mode, use the command config-t to go to global configuration mode. In global configuration mode, use the command spanning-tree UplinkFast. Also, you can display UplinkFast status with show spanning-tree UplinkFast from privilege mode. In addition to Portfast and UplinkFast, there's BackboneFast. BackboneFast speeds up convergence when non-directly connected links fail. It recognizes a link failure when it receives a BPDU declaring a switch as root with a higher bridge or path cost than the one it currently holds in memory. This is called an inferior BPDU, and it indicates a link has gone down and re-election of the designated bridge has taken place, indicating a link failure. Cisco recommends this feature be enabled by default on all switches to improve STP reconvergence by shaving off as much as 20 seconds from the normal 50-second convergence time. Here's an example of using BackboneFast. First, from user mode, use the command enable to go to privilege mode. In privilege mode, use the command config-t to go to global configuration mode. Inside global configuration mode, use the command spanning-tree BackboneFast. You can also display a BackboneFast status with show spanning-tree BackboneFast. Now let's examine Rapid Spanning Tree Protocol, or RSTP. In contrast to Cisco's proprietary Portfast, UplinkFast, and BackboneFast features, RSTP is a new IEEE 802.1W non-proprietary standard that can be implemented on switches from multiple vendors. It implements, in a generic fashion, many of Cisco's best features. Here's an example of using RSTP. From user mode, use the command enable to go to privilege mode. From privilege mode, use the command config T to go to global configuration mode. Once inside global configuration mode, use the command spanning-tree mode rapid-pvst to implement RSTP. Let's take a look at Ether channel. Ether channel bundles redundant links to aggregate them into a single logical connection. Cisco's implementation of this is known as Port Aggregation Protocol, or PAGP. The generic version of this is an IEEE 802.380 standard known as Link Aggregation Control Protocol, or LACP. Here's an example of configuring Etherfast on a non-root switch. From user mode, use enable to go to privilege mode, and privilege mode, use config T to go to global configuration mode. In global configuration mode, select a port or a range of ports, and then use these commands: switch port mode trunk to specify a trunk port, switch port non-negotiate, and channel-group 1 mode desirable. You can display Etherfast status with show, int, and then a port and ether channel. Note, the non-negotiate option stops switches from auto-detecting link type, since this would interfere. Here's another example of configuring Etherfast on a root switch. From user mode, use enable to go to privilege mode, and privilege mode, use config T to go to global configuration mode. In global configuration mode, use the command int port-channel 1 to specify the interface, and then select either a range of ports or a port. Then use switch port trunk encapsulate .1q, switch port mode trunk, switch port non-negotiate, channel-1 group 1 mode desirable, and switch port mode trunk. Again, you can display Etherfast status with show, int, port-channel 1. Here are some diagnostic and display commands that you'll find helpful. Show MAC address-table will display the contents of the switch's MAC address database or forward filter table. Show spanning-tree will display the root bridge and VLAN priorities. And then there's show spanning-tree VLAN 5 or another VLAN number to display STP information for a particularly selected VLAN. Now let's look at some of the security features available on Cisco switches, namely port security. Port security can shut down ports and notify administrators when a user connects a device with an unauthorized MAC address that feeds into that port. You may also specify that only one MAC address, once learned, can be used on a particular port. By setting the sticky option, the MAC address of the first device plugged into that port becomes locked and sticks until you manually change the setting, or any aging process you have configured automatically expires that MAC address. Here are some examples of configuring port security. First, from the user mode prompt, type enable to go to privilege mode. In privilege mode, type the command config T to go to global configuration mode. From global configuration mode, select an interface, say port 4. Then use these commands: switch port, port-security maximum 1 to specify that only one MAC address is allowed on that port, or switch port, port-security MAC-address sticky to turn on the sticky option. In this way, the first device plugged into the port, once its MAC address is learned, will be the only device allowed to that port. Use the command switch port, port-security violation shutdown to specify that a port should shut down if an unauthorized user plugs a laptop or other device into that port that does not have the designated MAC address. In this way, users can attach devices without an administrator knowing about it or allowing it. Let's look at the Catalyst switch's light-emitting diode patterns. When you see orange, the switches in learning phase are seeking STP convergence. When you see green, the port is operating normally. And when you see alternating green and orange blinking, that means the port is experiencing errors. There are multiple methods of connecting to Catalyst switches. The most common method is the console. For Cisco 3560, 3550, and 2960 switches, the console ports are located in the back. You can connect to these console ports with the laptop using a USB to 9-pin RS-232 serial adapter and a DB9 to rollover cable connection, as you would with Cisco routers. Also, you can use a web browser. In addition, like using SDM or the Security Device Manager on routers, Catalyst switches also provide a web interface over HTTP. You may also use Telnet once you've configured the switch with an IP address. Remember that to do this, just as with routers, you must enable the virtual terminal password and login. in this case VTY015. And then there's also the Cisco Network Assistant, or CNA, which you can download from their website. Finally, one of the unique and interesting features available on Cisco Catalyst switches is Power over Ethernet, or PoE. This is a feature that allows phones and access points to receive power from a switch by being connected to a port on that switch via an Ethernet cable.